morning, everyone. My name is Huang from AMD Linux GPU platform team, and works for the AMD GPU related software support in many years. And in recent 3 years, I focus on the GPU Para-Virtualization for graphics and the ROCm compute solution. So I'm very happy to join the Xen Summit again to continue talking about the updates of the GPU Para-Virtualization topic this year. In last 2 years, we kick off the pass-through GPU and the virtual GPU support with on the VirtIO and the Venus on Xen. And this is the first prototype to complete support OpenGL and the Vulkan 3D libraries based on Xen.
There seems to be some echo in this room.
Introduce
the remote audience people are saying
virtual GPU native context.
This is the room that
instead
we're
of
talking.
Lexi, VirtIO, and Venus for common virtual GPU.
Your any mics that are open,
started to prototype their
no, both are
the
muted.
AMD ROCm support on them. ROCm is a machine learning compute stack for all the AMD GPUs. And however, the basic the OpenGL and the Vulkan functions probably cannot meet their current automotive requirement. So this year, we continue to introduce some advanced features in this area. And questions and comments are welcome for me. Yeah. Okay, these are our team members. They are working on this solution. We are from Shanghai and Beijing, China, and work closely with the Perfetto team to deliver this solution. And the names with highlight was Penny, Jichen, and also
the mics are muted.
They are
Do I need to
working
check
on
something on the
kernel,
other
QMU, and Xen. They are not only delivering the GPU Para-Virtualization on Xen, and but also contribute the Xen safety function solution for automotive area together with the Stefano's team as well. And other guys like the the Trigger, Julia, Wei, Kerr, Jimin, and Yuling are many work on the GPU graphics and the display virtualization for automotive infotainment system. And Linshan Honglei and Junhua are working on the GPU compute for AI, the machine learning use cases, both on the AMDGPU and all the GPUs. And it's very great to see more and more numbers to join together with us. Okay, please take a look at this agenda. And first, I want to share the background of this solution in case they will still have a new member to join the summit this year. They want to know some history information as well. And then look back the virtual native context design for the OpenGL and the Vulkan in domain U guest. After that, we are introduce the new GPU recovery with virtual GPU in domain U, and the Mesa Perfetto tool for debugging and tracing in the second. And then we can help that can help the developer to understand the data flow at runtime. And the last two topics, they are mainly about the ROCm and the compute support. The first one is multiple context support for AMD KVD driver and the ROCm runtime on virtual GPU instance. These two for support the GPU compute with AI with virtual GPU in the Para-Virtualization. Okay, let's see the background. Last year we introduced the basic graphics and the compute functions based on the virtual GPU, and there is nothing enough. But there is nothing enough for the automotive requirements so far, according to some practice. And we continue working on some advanced feature like below in the modern cars. The first is the GPU recovery solution. As we know, the automotive has very high the safety requirement even in the graphics part. Once we encounter the GPU hung or hardware hung, it's not good to reboot the whole system. And that will cost a lot of time. The first method is we can do the GPU reset with GPU recovery to restore the graphics hardware functions independently instead of rebooting the whole system. And since the VirtIO GPU native context is functional, developer would like to have a tracing dump and performance counter calculation in the system. And so we added the Perfetto support on Mesa, AMDGPU Vulkan with native context approach as well. And then we can see a clear the performance counter changes and the detail function, like the the command buffer tracings in graphic side, such as the Vulkan and the OpenGL, and something like that with the Perfetto support. And we will continue to introduce the multiple context support in AMDGPU driver. That's to resolve a fundamental issue. Once we do the AI, let's say the problem is the issue is the one GPU context per one process. It works very well in the bare metal, but once we move to the virtualization system, they will have some limitations. So we have to make this kind of feature. I will introduce the details next step. And the last is we will introduce the VirtIO GPU backend into the ROCm runtime. And there is a ready support in the formal ROCm stack. The AMD ROCm stack is a similar software ecosystem like the CUDA for the GPU AI support. Okay, look back the history about the VirtIO GPU native context. I introduced the topic last year. In traditional, the VirtIO and Venus is not sensitive by the performance requirement. It will has very high the performance overhead on the host of Mesa. So then we introduced the native context with AMDGPU on Xen to address this issue. The designs are initialized by the community, the Rob Clark in last XDC on the Chrome system. So we leverage the idea to use the new native context method to forward the native libdiam API to the forward the libdiam API from get to host site to support the Mesa, the RadeonSi, and the Radv driver about Vulkan. And up level, we will continue to implement the Gaster, the VLAN, Western compositor tier to the 3D applications. Yeah, from this is the basic way to we do the graphics basic function last year. Most of the change already upstream. For example, the Mesa and the virtual render. AMD support are already merging into the main line, and only the QEMU is still in progress. And the QEMU will managing to introduce bulk memory. Bulk memory is the video memory. It's similar with the video memory in the guest. So it is hard requirement for the VirtIO GPU on AMD GPU as well. So we need to introduce the bulk memory support in the VirtIO GPU emulation at the QEMU side. Okay, let's start off the GPU reset. This is a hardware reset on AMD GPU. I need to introduce some hardware method here before we introduce the software GPU recovery. And the first GPU hardware reset is a software reset. The software reset is very lightweight, and the target is to reset the specific GPU IP blocks and just clear the register status, and only can fix very few issues. So is mainly used for the clear register states during the hardware initialization. And the second reset is a procure reset. The GPU procure reset is the fine-grained GPU recovery action. Driver only reinitialize only one issue of hardware queue, maybe the graphics, maybe compute, maybe the SDMA queue, and leave other queues and their engines running regularly. So we only will reset one queue and leave other queues running continue running and works well. And this is a lighter named reset entire engine. And the third method is the mode 1, mode 2 reset. This is the whole ASIC reset. We probably will reset most of the IP function blocks, like the graphic, compute, SDMA, and doorbell, and some context status, something like that. During this phase, we may lost the VRAM during the hardware reset and reinitialize the VRAM during this phase. So the time, the reset time, it's top to down, it's longer and longer. So in regular process, we will do the software reset first. If the software reset fail, cannot be resolve the issue, we will do the procure reset. That means the procure per-ring reset. Once the per-ring reset fail, we will do the ASIC reset, like mode 1, mode 2, till the hardware issue can be fixed finally. So there are 3 types of protection here. This is the hardware background, and and I need to highlight the enhancement of the procure reset here. And these patches are from our GPU maintainer. Alex is working on the improve the procure reset. We expect most of the fail case can be recovered by the procure reset. And while the reset triggers the software GPU scheduler, that's per-ring, the per-ring drop timeout. The recovery is affected current the ring or queue. We were firstly, if it is in the ROCm stack, the KFD will try to do the procure eviction, and only offending the process of the queue is a reset. That means only the guilty and the issue queue will be reset. Traditional, the testing only focus on the current queue. They won't impact another queues in the generic GPU. So it is very smallest the scope we can kill. We only need to kill. And the benefit of the procure reset is a minimal disruption and they're very fast. And we don't have the VRAM lost. And but they still have some limitations, because in some of the case, we have some sharing block. For example, one queue depends on another queue. So we only reset one queue. That probably cannot be recovered or resolve the issue. So we have to reset all every queues like the ASIC reset. So that means the procure reset also cannot be make sure they're 100% successfully in the in the AMDGPU, but they can resolve most of the case. And this is about the kernel side. But from the user space, we still have some issue need to once we were running some 3D applications, the kernel can reset successfully, but the 3D applications running in the user space, we will try to make sure the desktop is always valid and not be crash in the at the wrong time. So this is the user space manning for the ASIC reset, like the first mode 1 reset in the discrete GPU and mode 2 reset in APU. Mode 1 and mode 2 reset, they have some a bit difference. And the DGPU is we only do from trigger from the PCIe, because the discrete GPU is instead of PCIe bus. But APU system, in APU system, the iGPU is not connect the PCIe directly. They actually together with the CPU together in a hyper translation bus together. So we cannot do the PCI, the simple PCIe to recover the APU. That means the iGPU. So we implement another, the mode 2 reset for the APU system. This is the difference with the DGPU and the APU. And let me introduce some two user case. We were addressing the software, the up level. Please see the use case 1, and we will see the context A, B, C, D. The context A, B were mapped to the different the process from the user space, and they are from different, maybe from different job, maybe from the same job, but they were issued together into the same ring from the DRM schedule jobs done, and once we have a broken issue, like this is a guilty context, maybe this context may trigger the GPU harm. We will identify this is a guilty context, and once a group of context, there is one of context is guilty, then the Mesa will kill all of them in the same ring. That means if there is a easy, a simple 3D application, will be have some issue to trigger the GPU harm. All the 3D applications, maybe the 3D application is a graphics desktop. Maybe the 3D application is a QEMU. Once the good context is the QEMU and the 3D desktop, they will be killed together with the guilty context. So that will trigger the problem. Once we had the GPU kernel can resolve, but the graphics desktop will be crashed finally. So we cannot, in this case, the graphics desktop cannot be resolved successfully. So everything, you can see the context A, B, C, D will be all crashed. But actually the context B, C, D is good, but they will be killed at same time. So this is one of the problem. And let me see please see the second user case. And the context A, B, C, they were in the same they were in the same queue for submission. The context A will be guilty, but only the same queue as A, B, C, D will be killed finally. And the context D, they don't issue the command in this queue, so they can survive finally. So that means in some of the case, we will face the randomly issue. Maybe the graphics desktop can be randomly to be killed, because sometimes they made the context D, the graphics desktop, or QEMU made context D, so they will survive. So in these two user case, we will face the graphics desktop will be randomly killed, even there is no issue of a graphics desktop during the GPU reset. So we introduce a method to resolve the two user case for the GPU recovery in the VirtIO GPU side. And the first, we will make sure the graphics desktop. The graphics desktop is managed by the Western compositor. If we work for the graphics, you will see the compositor is very important to manage the graphics desktop. And we will introduce the robust context port in the Western compositor to make sure the Western desktop is always valid. Even they are in the same queue. If the Western context is robust, they won't be killed in the protocol. And And the workflow is we will create the context with the new the geo extension with robust list, and for geo render, and we will check the whether it is requested by a GPU reset. If yes, the destroy, we will destroy the current the context and recreate the geo and the easier context and the resource during the GPU reset. So we can restore all the surface of the client applications. So with this kind of flow here, the graphics desktop was always valid in the system to make sure the host side we have a good graphics. Even we can get successfully from the hardware GPU reset, and the patch sets almost be upstream, and this is the we already almost a step in the latest version of the Western compositor. And once we keep the Western, the host desktop is always valid, and we will make sure we still need to, in the virtualization system, we still need to indicate the robust context for the QEMU and the virtual render and the SDL as well, because in para-virtualization, the QEMU will be treated as a very simple OpenGL application. So they also can be one of the context as a graphics context as well. So we have to introduce the robust context in the QEMU, also the SDL and also the virtual render in QEMU as well. And because in case the QEMU context is in the same ring with Qt context, the QEMU process will be killed at that time. So that's the problem. And you will see here, we identify there were 3 contexts in the QEMU. Will be graphics context in QEMU, and the virtual render will be created. And then they need to add the one of the robust contexts. The first is the VK, the Vulkan. Oh, sorry, this is the virtual render, the context, and another is the virtual renders EGL context as well. And the third is the SDL context. We need to add the robust context for these 3 contexts as well, to identify the robust for these 3 contexts as well. So once we encounter the GPU reset, all of the 3 contexts will be recreated, destroyed and recreated. So with this way, the QEMU and the virtual render and the SDL will always valid once we do the GPU reset, because the QEMU and it's a very, very simple OpenGL application. They almost never can trigger the GPU hung. The 3D application can trigger the GPU hung. They are most of the very heavy 3D application, something like the gaming, something like the high-end and 3D benchmark or something like that. So we have to identify to some basic applications with robust. Then we can resolve the issue finally and make sure the GPU recovery can successful based on the para-virtualization, even on Xen. Okay, the second is the Perfetto support. And okay, what is Perfetto? Perfetto is a website UI application that can be identified the GPU traces and some system recording some system level and application levels traces. It is very useful for debug for debugging. We develop a PPS producer for AMDGPU, and this is a system-wide demo of the Mesa and used to collect the global performance counters. And please see the picture. And we will set the data source first, and initialize performance counter, and do some graphics, the GPU performance counter here. We also will introduce add the trace event to dump the performance counter in the Mesa driver. The Mesa driver will talk to the kernel to get the GPU specific performance counter value here. So this is the picture. We capture all the GPU relative the performance counter, so we can get the performance tuning with this tool to get some detailed data to tune in the performance of GPU. And another is the render stage of the Perfetto. And the Mesa has their own GPU performance tracing framework, which the driver choose to implement the GPU render stage producer for the Perfetto. Tracing is based on the U-trace. U-trace is very useful, and which needs a quick identify performance bottleneck. And we were build a tool and analyze the raw performance data. And the main trace, they have 3 steps. The first step is adding the trace point for the Radv and the RadeonSi driver, and we can get the recording the trace point and submit a new job to handle the callback functions once the render stage event issues. And please see the blocks. The third is implement to the U-trace jobs here. So I don't describe the more details here due to the time is tight. And let me go to the picture. We can dump all the command buffer trace inside of the GPU here. So developer can dump all the data package inside of buffer from the list tool. So it's very useful for debugging, and the user can monitor is there is something wrong in the detail GPU command for AMDGPU here. Okay, let's go to the machine learning about GPU side. And the first is the KFD driver. This is the current issue or challenge we are facing. The single context per process in KFD driver. You can see the picture here, and the KFD driver, one of KFD process were mapped to one GPU VM. That means in host side, we are go to the one process only can have one virtual address space, but from the native context and para-virtualization, the kernel is running in the host, but the user space is running in the QEMU or virtual machine. But if the one if the process or different application in one guest VM, they will always go with QEMU to GPU VM. That means if there is a program 1, program 2, program 3, program N, program 4, and there's something like that, they will always share one GPU VM. That's the problem, because by design in bare metal, we only will map one process to one GPU VM. But here we have a multiple process. They were sharing the VM, so they will have a security issue. They will attack each other. Because the programming 1 may override the programming 2, the process. So that's the problem. So we have to redesign and the KFD driver to support the multiple contexts per process. So this is the new the change for the KFD driver. We actually already finished and go to the upstream at this moment to support the one GPU VM in the cost, a different GPU VM in the host side. They can map into the detailed program inside of one inside of virtual machine with the FD, different FD, and the passive isolate from their IOVA address space. So with this the new design, even the process inside of GPU VM, inside of virtual machine, they can only own one GPU VM in the host site. They can isolate successfully, and they won't attack each other. So this is the new change and design. We reorg the GPU, the KFD driver in the for the ROCm side to support the new way and in the para-virtualization stack. And also we need to some corresponding the multiple contexts in the user space as well. We will address the FD and the wrappers in the sunk driver for the ROCm side. Okay, the second big feature is we introduced the VirtIO GPU backend into the ROCm runtime to support AMD ROCm for para-virtualization. And the first, this is the original way to the pass-through. The KFD driver kernel is running the guest, and they will go with the traditional the sunk and the ROCm runtime, the KFD driver in the GPU urgent to support the next way. And this way is the new for GPU para-virtualization. The KFD kernel is running in the host site, and we will go with the VirtIO GPU here. They based on the Xen, and we will introduce VirtIO GPU backend into the ROCm runtime and sunk interface to implement API forward from sunk to the guest driver. We will introduce the new VirtIO GPU KFD driver backend into the ROCm runtime. So this is our way to support the ROCm in the para-virtualization. Then we can, I will go faster. Here, okay, this is the last picture. We were adding the host side for introduce the sunk rendered context. All the API forwarding is in the guest. They should be come from the host side. So we introduce the sunk render context inside of virtual render. Then they can forward the sunk in API for the AMDGPU, the compute stack to the guest side. Yeah, and also the patch is in progress for upstream. You can check the detail in the virtual render implementation here. All right, last. In the last page, we are still working on some new features to continue support the GPU virtualization based on Xen. The first is a multiple overlay. It is for display virtualization. That is still in progress. Maybe I can introduce in next time. And the second is a heap for ROCm for virtualization based on ROCm stack. And the third is we are planning for some safety support due to the ROCm. Maybe we can address some automotive the requirement. And the most important is the fourth. We will introduce the Windows guest DOM-U to support 3D virtualization here. It's very useful. Then once we gather the Windows guest here, our GPU para-virtualization is complete. Okay. And these are the reference here. Okay, I would like to take some question, or the time is out.